Welcome to CS 1401 Video 20.1. In Video 19.2, we looked at implementing algorithms in Prolog with particular attention to arithmetic algorithms, such as factorial, that we've already seen implemented in Java. In this video, we'll look at algorithms for operations on lists, including some algorithms that we've already seen, such as last, which returns the last element of a list. I'll also discuss three other list algorithms, such as count, which returns the length of a list. Prolog has built-in support for lists, and the syntax is simple. Here's an example of a list. A left square bracket indicates the start of the list, commas separate the elements of the list, and a right square bracket indicates the end of the list. Square brackets without contents represent the empty list, which is the same as null. In this example, the number 4 is the head of the list, and the tail of the list is the list 5, 6, 7, 8. In this example, the head of the list is dog, and the tail of the list is the list cat, sheep, lion, sheep, rhino. And in this example, the head of the list is blue, and the tail of the list is the empty list. Prolog has a convenient syntax for the head and tail of a list. A vertical line separates the head and the tail. So the list 4, 5, 6, 7, 8 can also be written as 4, then the vertical bar, then the list 5, 6, 7, 8, because 4 is the head of the list, and the list 5, 6, 7, 8 is the tail of the list. This makes it convenient to write recursive algorithms because we can write h vertical bar t to match any list with at least one element. The vertical line in the representation of lists is called the list constructor because it's the building block for lists. While the representation with commas is a convenient way to write lists, for example, blue, red, yellow, the same list can be written with the list constructor as blue, vertical bar, then the list that starts with red and whose tail, indicated by the vertical bar, starts with yellow, and the tail of that list is the empty list. And this shows the underlying structure of the list. I've written two Prolog clauses that work similarly to the head and tail methods I wrote for lists in Java. You don't really need these in Prolog because the representation of lists in Prolog provides this directly, but my head and tail clauses will let us see clearly the structure of lists in Prolog. The clause head has two arguments, a list and the head of the list. If the first argument is bound to a list, then the variable h will match the head of the list, the underscore will match the tail of the list, and the second argument will be unified with the head of the list. For example, calling head of 4, 5, 6, 7, 8 as the first argument and x as the second argument returns true with x equals 4. Similarly, calling head of the list with one element blue with x as the second argument returns true with x equals blue. The clause tail also has two arguments, a list and the tail of the list. If the first argument is bound to a list, then the underscore will match the head of the list and the variable t will match the tail of the list. And the second argument will be unified with the tail of the list. For example, calling tail of the list 4, 5, 6, 7, 8, x, will return true with x equals 5, 6, 7, 8. Similarly, calling tail of the list with one element called blue in it, x, returns true with x equals the empty list. Okay, so that's how Prolog represents lists. Let's get started on working with lists, starting with the algorithm for last. I'm going to call my program myLast because Prolog has a built-in predicate called last. There are only two clauses in the program. The first is the base case. If there's only one element in the list, then the second argument should be unified with that element. So my last of the list containing x means that the last element in the list is x. The second clause is the recursive case. If there's more than one element in the list, then the last element must be the last element of the tail of the list. So I'll recursively call my last on the tail of the list. The second argument will be unified with the last element of the tail of the list, and that means that x in my last will be the last element of the list. What if the list is an empty list? Well, then my last isn't going to match in either of its clauses, and my last of the empty list will fail, which is exactly the behavior we want. Let's try it out. First, let's try my last on the list 4, 5, 6, 7, 8, 9. And correctly, the program executes so that x gets instantiated to 9. Next, let's try it out on a list with exactly one element. And that works correctly. And finally, let's try it out on a list that's the empty list. And just as we wanted, Prolog returns false. Next, let's look at a program that returns the length of a list. I'll call this program count. Count also has two clauses. The first clause is the base case. And logically enough, if the first argument of count is the empty list, then the second argument, which is going to be the number of items in the list, will be 0. The second clause is the recursive case. If the list isn't empty, then we don't care what the first element is, but we'll count it. So we'll call count on the tail of the list, that's L, and instantiate M to the number of items in the tail. So we'll instantiate n, that's the count we're returning effectively, to be m, that's the number of items in the tail, plus 1. Let's try this out. First, let's try count of the empty list. And it correctly returns that x equals 0. Next, let's try a list with one element in it, and x is correctly set to 1. And finally, let's try count with a list with 5 elements in it, and sure enough, Prolog returns true with x bound to 5. What if we don't want to count all the elements of a list? Maybe we just want to count some elements. For example, if we have a list of animals, we might want to count all the occurrences of sheep. So here's a program named CountSheep that calculates the number of times that that word appears in a list. The program for CountSheep has 3 clauses. The first clause is the base case. Not surprisingly, if the list is empty, there aren't any sheep in it, so the second argument should be 0. The next clause is the case where the first item in the list is the atom sheep. If that's the case, then I'm going to want to make the count equal to 1 plus the count in the rest of the list. So I call CountSheep recursively with a tail and a variable called tc for tail count. That will instantiate tc to the number of sheep in the tail of the list, and I can add 1 to that and instantiate count with that new total. The third clause is the case where the first atom is not a sheep. So in that case, all I need to do is count the number of sheep in the tail and make that the count for the list as a whole. Let's try out CountSheep. I'll try out my program with the list dog, cat, sheep, lion, sheep, rhino. And I'm expecting that when Prolog executes, it will instantiate x to 2. Let's give it a try. sure enough, that's the result we got. We don't have to limit our counting to sheep. It would be possible to write a really similar program with 3 arguments, where the second argument is the thing to be counted. So you could call count items of the list, then an atom or number, the thing to be counted, and then a variable for the count of those items. You might try writing that program as an exercise. Finally, we'll look at a classic algorithm, the Prolog implementation of member. The idea here is to determine if something appears in a list. If that thing is a member of the list, then return true. Otherwise, return false. This is what we called in our Java implementation linear search. Here's the Prolog code for member. The base case is if the item is the first element of the list. That is, member of X is true if X is the first element of a list, and we don't care what the tail is. The recursive case is true if X is a member of the rest of the list. It doesn't matter what the first element is because it's not matching. So we'll return member of X and the tail of the list true if X is a member of the tail of the list. Again, member of X and the empty list will return false, so we don't have to put that in as an explicit case. Let's try out member. As a test case, let's see if the atom sheep is a member of the list dog, cat, sheep, lion, sheep, and rhino. I'm expecting Prolog to say that this is true. And it does. Next, let's see if tiger is a member of that same list. I'm expecting Prolog to say that this is false. And sure enough, it is false. Finally, let's check the case where we're looking for an item in an empty list. In this case, let's see if sheep is a member of the empty list. And Prolog correctly reports that this is false. Well, that's a look at 4 programs in Prolog that work recursively with lists. In video 20.2, I'll present 4 more Prolog programs for lists. I'll see you shortly.